Welcome to the lecture on electric potential part 2. In this lecture, the intended learning outcomes are to calculate the electric potential due to a continuous charge distribution, determine the location of equipotential surfaces, analyze electric potential at the surfaces and inside a charged conductor. So one of the key vocabulary terms that you're going to learn today is the equipotential surface. So let's start with the topic electric potential due to a continuous charge distribution. Before we start discussing electric potential due to a continuous charge distribution, let's recall some of the basics that we learned from the previous lecture regarding the electric potential for a point charge. So let's say that we have a point charge Q and we want to find out the electric potential at point P, which is at a distance r from the charge. Now we've learned that electric potential at this point is equal to K Q over R. Now we also learned that if you have a collection of charges like Q1, Q2, Q3, which are located at distances R1, R2, and R3 from this point P, then the electric potential at this point P would be simply an algebraic sum of all the electric potentials created at this point P due to all of these charges. So the electric potential at point P would be equal to K sum of all the Qi over Ri. So where I is changing from 1 to n, if we have n particles. So this is what we had for an electric potential for a discrete number of charges. Now, what if instead of a discrete number of charges that you can count, what if you have now a continuous charge distribution? So let's draw a picture for a continuous charge distribution that looks like this. So it is some kind of 3D shape, and let's say that it has some charge which is distributed over the entire volume of that three-dimensional object. Well, the charge doesn't have to be distributed uniformly, but let's say that we divide this 3D shape into small pieces, and let's look at one small piece. Now that small piece will carry a small element of charge, dq. So it's an infinitesimal piece of that object. And let's say that it is at the distance r from point P. Then the equation that we have for electric potential of a point charge will change. Now we can talk about the electric potential element created at this point due to this element of charge dq. So instead of Vp, I can say dV, and instead of q, I will have dq. So this is how the equation changes for an element of charge. It is similar to what we did when we were considering electric field due to a continuous charge distribution. So same thing is here. Now instead of a collection of charges, you have a continuous charge distribution, and if you want to find the effect on the electric potential at point P due to the entire charge distribution, instead of having an algebraic sum like this, we will have an integral. So the electric potential due to this continuous charge distribution would be K integral of dq over r over the entire charge distribution. Now, in actual problems, we will be dealing with some symmetric charge distribution, and we will also be considering, different kind of problems like 3-dimensional, 2-dimensional, and 1-dimensional. So let's look at each one of them individually. Let's say we have a 3-dimensional problem. For a 3-dimensional problem, this charge dq can be represented as charge density multiplied by the volume element, dV. Okay, so here let's use a slightly different symbol to make sure that it's not confused with the voltage. So this is volume, element of the volume dV. And this charge density rho is the regular charge density measured in coulomb per meter cube. So this is volume charge density. Okay? If we have a 2-dimensional problem, in other words, if you have a surface of some sort, then the element dq on that surface will be represented as surface charge density times the area element dA. So the sigma would be the surface charge densities coulomb per meter squared. And finally, if you have a 1-dimensional problem, then this element dq will be represented as linear charge density times dA, where lambda is coulomb per meter. Now, whenever you have a problem on continuous charge distribution, you always have to take advantage of the symmetry of the problem. Just as we did in the problems with electric field due to a continuous charge distribution. However, finding electric potential is actually much easier than finding the electric field due to a continuous charge distribution, because electric potential is a scalar. This is a scalar value, and so you don't need to worry about any directions here. So that's an advantage. So let's look at some examples. So let's look at this simple example. Let's say that we have a line of charge which is extending on the x-axis from x0 to 3x0. And let's say that the charge is distributed uniformly with the charge density lambda. The question is, what is the electric potential at the origin here? So again, the charge is extending from x0 to 3x0. And it's a uniform charge distribution with the charge density lambda. Well, let's consider a small element of charge which is on that small element of that rod. So let's say that this length is dx. So the amount of charge that's on this dx is equal to dq, which is equal to lambda dx. This element dx is at the distance x from the origin, which is a variable. And so the contribution to the electric potential of this element dx at point O is equal to k dq over x. So we can substitute, we get k lambda dx over x. So what is the electric potential of V0 then? Well, we just need to take an integral. So V0 is then equal to an integral. K lambda is a constant, so it just comes out of the integral. Dx over x. And remember, the charge is extending from x0 to 3x0. So the limits are from x0 to 3x0. Integral of dx over x is a natural log. So you get k lambda log of x from x0 to 3x0. This is equal to k lambda log of 3x0 minus log of x0. And finally, this is equal to k lambda log of 3. So v0 is equal to k lambda natural logarithm of 3. Let's look at another example. Let's say that we have a ring of charge with a total charge q and radius a, and we want to know an electric potential at point P, which is at a distance x from the origin. Well, just as it was in the previous example, let's look at a small element of charge located on this small element of the ring. So let's say that the amount of charge that's here is equal to dq. This small element of charge dq will contribute a small element of the electric potential dV at this point. So this small element of electric potential dV at point P is equal to k dq divided by r, where r is this distance. Well, just by looking at this triangle, you can see that r is actually equal to a squared plus x squared square root from the Pythagorean theorem. So we can take it and substitute it here. So we get k dq x squared plus a squared square root. And so the total electric potential at point P is then equal to integral of this. Now note that every point on the ring, because of the symmetry of the problem, is exactly at the same distance r. So this distance r is actually a constant for every point on the ring. So when we take an integral, the denominator comes out of the integral, so we get k x squared plus a squared square root, that's a constant, integral of dq over the entire charge distribution. So this is equal to integral of dq is just total charge q. So we get k q over x squared plus a squared square root. Okay, so let's remember this result, as we're going to need it for the next problem, which will be a little more complex. Okay, so in this problem, again we have a symmetrical charge distribution, but now instead of a ring, we have a disk of charge with the same charge q, which is uniformly distributed across the entire area of that disk. So the question is, what is the electric potential at point P again? Well, we've already seen this kind of problems when we were solving electric field created by a disk. So now we will use exactly the same approach. So we will consider this circular disk as a collection of rings. And let's look at one of them. Let's look at a ring that has a radius r and that has a thickness dr. Okay, now if we want to find the electric potential created by this ring at this point, we can use the result from the previous example. So let's write down the result from the previous example. So in the previous example, we said that electric potential at point P due to a ring of charge was equal to K x squared plus a squared times Q. So this is the result from example 2. However, we can't use this example directly. We need to modify it a little bit. Well, first of all, instead of talking the electric potential Vp, we have to talk about an element of electric potential, dV, because it will be a contribution of from one single ring. So instead of Vp, we can say dVp. K divided by, and remember this was a distance, and actually there is a square root here. This was a distance from the point on a ring to point P. Well, now it will change a little bit. This distance is still equal to x. So this is x, but this distance is now equal to r. So instead of a, we put r. So this becomes x squared plus r squared 1 over 2. And now instead of big Q, we have to talk about a small element of charge Q. So the amount of charge on that ring is, let's say, dQ. Okay, so let's substitute that in. dQ. So now we need to work out, well, how much charge is here on the ring, dQ. So this dQ is equal to the sigma, the surface charge density, times the area of that ring. So the area of the ring is equal to the circumference, which is 2 pi r, times the thickness, dr. What about sigma? Well, sigma we can find from the total charge and the total disk area. So the total charge is Q. If we divide it by the total area, that is pi a squared, that will be our sigma. 2 pi r dr. Well, you can cancel pi, and so you get 2q over a squared r dr. So we can now take this dq and substitute it here. So we get dvp equals 2kq over a squared r over x squared plus r squared 1 over 2 dr. So we get this element of the electric potential, and now the question is, how do we integrate this? So the electric potential Vp is then equal to integral of this so from r dr of x squared plus r squared 1 over 2. And the limits of integration are from 0 to a. From 0 to a. In this course, you are not expected to be able to take these integrals, so you can just look them up from a textbook or from a table of integrals. And if you do, this is what you get. So you get this constant, 2kq over a squared, and the integral is x squared plus r squared 1 over 2 from 0 to a. So you can now substitute everything in. and you get V at point P is equal to 2kq over a square x squared plus a squared 1 over 2 minus x. This is one way of writing it. Another way, if you get rid of the of q, but and say instead of q, if you write sigma. So remember that q is equal to sigma times pi a square. If you substitute it in, you get 2k pi sigma multiplied by square root x squared plus a squared minus x. So either this form or this form works. So this is the electric potential created by a uniformly charged disk at point P.
So the next topic is equipotential surfaces. Let's consider an electric field. The electric field doesn't have to be uniform. So here on a picture we have electric field lines of a non-uniform electric field. Now let's consider an infinitesimal displacement such that it is perpendicular to one of the electric field lines. If the displacement ds is perpendicular to the electric field, according to the equation that we have here, dv equals minus dot product of electric field vector and displacement vector ds. According to that equation, E dot ds will give us 0 because the two vectors are perpendicular. So this means that dv is equal to 0. So if the differential dv is equal to 0, that is only possible if v is constant. So in other words, 2 points which are connected by this infinitesimal displacement ds, let's call them A and B, have exactly the same electric potential. It is the same. VA is equal to VB. So now if you connect these 2 points, and they're very, very close to each other, they're at an infinitesimal distance ds from each other, along that line the electric potential is the same. It's a constant. And this kind of line can be called an equipotential line because potential at every point on that line is the same. Now, however, this picture is a simplified two-dimensional picture. In reality, of course, we need to deal with 3D electric fields. So let's say that we have a three-dimensional electric field, and then instead of a line on which the potential is the same, the equipotential line, we now have an equipotential surface. And you can continue this displacements ds such that at every instant the displacement ds is perpendicular to the electric field. And thus you construct an electric field line at different locations. So then if you connect all of these points with a dashed line, you get an equipotential line. It's an equipotential line in a 2D picture, but in reality it's a three-dimensional equipotential surface. So again, the key things here is that on the equipotential surface, electric field is perpendicular to that surface, and electric potential is the same at every point on that surface. So let's look at some examples. Let's say that we have a positive point charge. Now we already know that the electric field lines are going in all directions away from that line, from that point charge. They are represented by these red arrows. So the red arrows are showing the electric field lines. And a surface which will be perpendicular to the electric field lines, in this example, you can guess it's a sphere. So these dashed lines represent concentric spheres with a center exactly at the location of a point charge. So each of these spheres represents an equipotential surface. Of course, this is a two-dimensional picture, so we're looking at a cross-section. But in reality, each of these circles is a 3D sphere with the center at the charge. So let's look at the first sphere here, the smallest one. At every point on that sphere, the surface of the sphere is perpendicular to the electric field lines, to these red lines. That's one thing. And the other thing, the electric potential, for example, at this point is the same as it is at this point. So if here it's 5 volts, then here it's 5 volts, here it's 5 volts, and here it's also 5 volts. So the electric potential on the surface of an equipotential surface is the same. Now let's look at another configuration of charges. This is the well-known dipole, where you have two opposite charges, plus and minus. The blue lines here represent electric field lines, and the dashed lines again represent equipotential surfaces. Again, this is a cross section, so we're looking at a two-dimensional picture. Just as in the previous example, again, equipotential surfaces are perpendicular. Here it is a little more difficult to reconstruct, but if you just keep in mind the fact that at every point equipotential surface is perpendicular to the electric field line, you can reproduce this kind of picture yourself. Now I'm gonna pause for a second and you try and work out a picture for equipotential surfaces of two positive charges. So imagine you have two positive charges at some distance from each other. Draw the electric field lines, and this is one of the examples we did in the seminar, and reproduce electric equipotential surfaces for this configuration of charges. So stop the video for a second and try to do that. And here is the result. So we have two positive charges separated at some distance. Blue lines again represent the electric field lines, and these dashed lines are the equipotential surfaces. As you can see, they look like number 8, which is turned 90 degrees. So this is an example of equipotential surfaces. Now let's look at one more example here. Here we have a positive charge and then a conductive sheet at the bottom. Now we haven't yet talked about electric potential on the conductive sheet, and this is actually one of the next topic of this lecture. Okay, so the next topic is electric potential due to a charged conductor. Consider a conductor of an arbitrary shape which has some excess charge on it. In this case, we have a conductor with some positive excess charge on it. Now let's say that the conductor is at electrostatic equilibrium. That is, the charges are not moving anywhere. There were a few things that we've learned from the previous lecture regarding a conductor with excess charge at electrostatic equilibrium. The first thing that we've learned is that all of the charge that is on the conductor is on the surface, on the outer surface of the conductor. The second thing that we've learned is that the electric field just outside the conductor is perpendicular to the surface of that conductor. Everywhere on the surface, the electric field is perpendicular to the surface. And we also learned that at electrostatic equilibrium, the electric field inside the conductor is equal to 0. So what are the implications of these things on the electric potential? Well, let's look at electric field on the surface of the conductor. If the electric field on the surface of the conductor is perpendicular to the surface, mathematically this means that the dot product of the electric field and ds vectors is equal to 0 everywhere on the surface, because the two vectors are perpendicular. Electric field is perpendicular to the surface, ds is parallel to the surface. So the two vectors are perpendicular to each other, and the dot product of them is equal to 0. The consequence of that is that if you choose any 2 points on the surface of the conductor, like A and B, as shown in the figure here, and if you find the electric potential difference between these 2 points, that is VB minus VA, which is equal to the integral of dV from A to B, which in turn is equal to the integral of minus E dot ds. We've already seen this formula before. Because the dot product of E dot ds everywhere on the surface is equal to 0, the whole integral is equal to 0. This means that VB minus VA is equal to 0, and so VB is equal to VA. So this is how we prove that any 2 points on the surface of a conductor will have exactly the same potential if the conductor is at electrostatic equilibrium. So VB is equal to VA. So we could have chosen any 2 points. So the conclusion is that electric potential is the same everywhere on the surface of the conductor. So this means that the surface of the conductor serves as an equipotential surface. So because the surface of the conductor fits the conditions for equipotential surface. First of all, electric fields are perpendicular to it. That's one thing. And the other thing, electric potential is the same on the surface of that surface. So it has to be an equipotential surface. Okay. Well, what about the electric potential inside the conductor? Well, we already said that electric field inside the conductor is equal to 0. So if you work out exactly the same integral as we did before, you will get the difference in potential between any 2 points within the conductor equal to 0 again. But now it is equal to 0 because the electric field is equal to 0. Which means that electric potential inside the conductor is constant. So any 2 points inside the conductor will have exactly the same electric potential. And that value of that electric potential will be equal to the value of the electric potential on the surface of the conductor. So these are the important conclusions as far as the electric potential of a charged conductor is concerned. So now let's look at a few examples.
Okay, so let's look at a simple example. Let's say that we have a charged conductor in the form of a solid sphere. So let's say that the solid sphere is carrying some excess charge Q, which is positive. Now we want to reconstruct the electric field strength as a function of R and the electric potential. Now from the previous lecture, and we have revisited this in this lecture, electric field inside the conductor is equal to 0. So we can show that, we can say that here electric field, if R is less than the big R, that is inside the conductor, the electric field is equal to 0. What about the electric field outside the conductor? Well, we already solved this kind of problem in the seminars and in the lecture before. We know that outside the charged sphere, electric field is identical to that of a point charge. And we know that for a point charge, the electric field is equal to kq over r squared. So graphically, it will look something like this. Okay, so this is the equation for kq over r squared, and at this point, it is equal to kq over big R squared. So this is now the electric field. Well, what can we now say about the electric potential? Well, if we want to find out the electric potential, then there are two ways in which we can do that. Let's use the integral. So we know that electric field is equal to k q over r squared. And this is when R is bigger or equal to the big R. So the electric potential difference, delta V, is equal to the negative of electric field dot dr. Now in our case, E and dr are pointing in the same direction, so we get this equal to minus kq integral of dr over r squared. And let's say that we're taking from infinity to some distance r. Okay, so from infinity to r, from infinity to r. Now, because we have r here in the limit, it would be better if we just put, a prime sign next to the variable, so dr prime. So this integral is then equal to k negative kq minus 1 over r prime from r to infinity. Minus and minus cancel out, you get plus kq 1 over r, that's the upper limit, minus 1 over infinity, that's the lower limit, and so overall you get kq over r. So you can say that on this side, when r is bigger than the big R, electric potential looks like this, and the dependence is kq over r without a square. We have just learned from the lecture that the electric potential inside the conductor is equal to the value of electric potential on the surface of the conductor. On the surface of the conductor, at this point, electric potential is equal to kq over big R. So the electric potential inside is exactly the same as it is on the surface. So this is how the graph looks like. Okay? So in this example, we are now given two conducting spheres of different radii, R1 and R2, and there is some excess charge, positive excess charge on the upper sphere, Q1, and some excess positive charge on the second sphere, Q2. The two spheres are connected by a conducting wire. Okay, so it is important that it's a conducting wire. The question is, what is the ratio of the electric field magnitudes at the surface of the first sphere and the second sphere? Well, we already know from the previous example that the electric field on the surface of a sphere, E1, would be equal to k q1 over r1 squared. So same thing applies for the lower sphere. So we can say E2, electric field on the surface of the second sphere, is equal to k q2 over r2 squared. So let's take the ratio of the two. So E1 over E2 is equal to, well, k will cancel out, so you get q1 over q2, r2 over r1 squared. Well, we also know that from the previous example that the electric potential on the surface of the first sphere, let's call it V1, is equal to k q1 over r1. Electric potential on the second sphere, on the surface of the second sphere, is V2 k q2 over r2. However, because this is a conductor, this is a conducting wire, and this is a conductor, we can think of this entire system as one single conductor. And because it's a one single conductor, electric potential at every point on that conductor is the same. So in other words, V1 is actually equal to V2. So from here, we get Q1 R1 is equal to Q2 R2. So the ratio of the charges, Q1 over Q2, is equal to R1 over R2. So we can use that and plug it in here. So this becomes R1 over R2 multiplied by R2 over R1 squared. So the final result is R2 over R1. So the ratio of the electric fields on the surface of these two spheres is only related to the radii of these two spheres and not the charges on them.
As a part of your self-study, we would like you to go through the chapters 25.5 and 25.7 in the textbook Physics for Scientists and Engineers.